Welcome back to Statics EGE 2013 at Lawrence Tech. I'm Jim, and as I've hinted about in a couple previous videos, we're going to go from a loading to the shear forces to the bending moments via integration without having to, cut sections and things. We'll just do it pretty much mathematically. We're going to do two examples. One would just be a cantilevered beam with a triangular loading on top of it. And then the other one, we will add this strut in here. We're going to use this airplane as a kind of a model, and we're assuming the triangular lift distribution. That's not a very accurate assumption, but this is statics, not aerodynamics, so I'm going to um, use a little bit of license here and simplify the math to make it easier to follow along and also easier for me to do too. So if we just take this and look at one wing, we have our simplified lift distribution, which I'm assuming to be triangular, and I have an equation for that where this is the total lift in pounds. B is the maximum value of lift, and I picked a value of 108 for that because that's basically just the number that works out to make this equation give me a number. I think the total lift came out to be 1,298 pounds, which is a reasonable number for this particular airplane operating, at straight and level flight. A is the wing semi-span, the length of one wing, which is 12 feet. X is our variable, which starts at 0 at the wing root. And so we have an equation for lift as a function of X with all the numbers, and that simplifies to just simply 108 minus 9X. So here's a diagram of the forces on our wing. The lift is pointing up, you know, and it has that triangular distribution. There's a reaction force here at the wing root that points down to counteract that, and of course the moment to counteract the bending moment caused by the lift. We have the equation for our lift from before. We're saying that the shear force is the integral of the load as a function of x plus some initial condition. And we're also saying that the bending moment is the integral of the shear as a function of x and then some other initial condition there, which we will find. Now, what we could do is find the initial conditions, or find the reaction forces, I should say, by solving our load, coming up with the equivalent load, which is going to be acting somewhere. Well, it's a triangle, so it'll be a third of the distance. It'll be acting there. We could find the value of that load, and that would tell us the value of the reaction force. That load times the distance tells us the value of that moment. And it wouldn't be hard to do because this is a simple triangle, but I'm going to avoid that. We're just going to run the math and see what happens and see if we get the right answers. And, if we had a more complicated distribution that wasn't so easy to just look up in the back of the book, we may not have that option of doing the simple way. So let's run the math. Now, I said that the shear is the integral of the load as a function of x plus the initial conditions, okay? So if I write that out, I can say that the shear load is equal to the integral of 108 minus 9x dx plus an initial condition. And the initial condition comes from the loading at x equals 0. If I do the integration, I get v equals 108x minus 4.5x squared plus initial condition. And I know that that the shear load, when I get all the way out here to the end, has to be 0, right? Because there's no forces beyond that. There's no nothing. It just everything fades away into the sunset. So I know that if I evaluate this at x equals to 12, this should be equal to 0, right? Because at the end my shear is equal to 0. So I get 108 times 12 minus 4.5 times 12 squared plus the initial condition equals 0. And when I run that all out, I get my initial condition equals minus 648, and the units here are pounds. I don't know that I mentioned that before. And if we had done the triangle calculation, we would have got the same answer. And so that tells us that this, if this is 648 downwards, somewhere in here I have some equivalent force equal to 648, but in theory we don't know where that is quite yet. And the other thing we should do is be careful with our signs. We have an upward force, and that's going to result in our downward reaction force. That's a negative force in our up and down convention. When we look at the internal loads, if we have a section of the beam here, we have the downward force at the left, there's some upward force at the right side, and some force due to the lift. And this is our shear, V, right? This results in a counterclockwise rotation here, so our shear force is negative at the root, okay? And then gets less negative as we go out. That gives us our final equation for the shear as a function of x equals minus 648 to give us that negative number right at the root, plus 108x minus 4.5x squared. And if I go to the next slide, there are the numbers we have so far. We have the equation for the loading. We integrated that. We got this equation right here. There's the graph of it. It starts out negative and ends up at 0, and it has a positive slope everywhere, so it's decreasing in magnitude. And I would point out that our linear loading, it's a straight line here, ended up, and it's a linear first order equation, ended up with a second order shear force. So given the shear, what is our moment as a function of x? Well, once again, our moment is the integral of the shear plus some initial conditions. So my moment is equal to the integral of minus 648 plus 108x minus 4.5x squared dx plus my initial condition, whatever that might be. So if I do the integration, I get minus 648x plus 54x minus 1.5x cubed plus our initial condition. And again, we know that at x equals 12, and I wrote at x equals 12, we know that the bending moment has to be 0 because, again, there's nothing out at the end of that beam or cantilever. So if I evaluate this at 12, I get minus 648 times 12 plus 54 times 12 squared minus 1.5, 12 cubed equals 0 plus my initial conditions. Sorry, forgot that. Um, and when I solve that out, I get minus 2592 plus the initial condition equals 0, which gives us an initial condition is equal to 2,592 pounds. And that gives me my final m of x. I'm going to put it up here. That gives me my moment as a function of x equals 2592 minus 648x plus 54x squared minus 1.5x cubed. Okay. Okay, so having determined our initial conditions and we found this 2592 number here, um, if we look at our beam and at x equal to 0, I've got a 2592 foot-pound moment, and it's acting in that direction because our forces are up, right? So I've got a reaction force which has to be clockwise, so that's a negative 2592, and we can fill that back in our other diagrams. The other thing to look at is if we have a beam segment and we have our reaction force at the end and we have our bending moment here at our section, um, these moments will tend to bend this up into concave upwards or our smiley face shape. So we know we have a positive moment, at least at the root, and at x equals 0, a positive number here for our initial condition gives us a positive result. So we're confident that our signs are just fine there. And finally, just as a double check while we're at it, we know that the moment is equal to the equivalent force. If we were to convert that triangular load into a single equivalent force, acting at some equivalent distance, okay? So I can rearrange that and say that the distance is equal to the moment. We just said our moment at the root there was 2592 divided by the force. Well, the force is that load we've applied, and I'm not too worried about signs at the moment. I'm looking for magnitudes. From the other side, that was 648. And if we divide that out, that gives us a distance of 4 feet, given that this is pound feet and this is pounds. Um, and if we look at our triangular load distribution, and we know this is 12 feet there, uh, our force is going to act at a distance 1/3 of the way, so it's going to act at 4 feet, and that's what we got. So, it's always nice to confirm our results. And the last slide on this, I've kind of put all the diagrams together. The top one is our loading. We've got the reaction forces, the moment, and the vertical load at the wing root calculated. We've got a equation for the shear force, and we've got that graphed out, and same thing for the moment. We've got an equation and a graph, and that's pretty much everything we needed to accomplish, given just simply this initial equation, the couple dimensions, and going through and integrating, which was our plan for the whole thing, right? So let's look at a more complicated example. When I throw that strut on there, a lot of things change. First of all, I have a force here, which is generated by the strut, and structurally, instead of having a fixed end like I would with a cantilever, I have a pin connection here, and there's a pin connection there as well at the strut, and that, by the way, corresponds to reality. In my airplane, there is a single bolt right there at the root that holds the main spar to the fuselage, and there's a single bolt right there at the strut that holds the strut to a bracket attached to the main spar. So our assumption is we'll have pinned joints, so there's no moments at any of these joints. That reflects the reality. We're going to have some force here at the root in the y direction, some force at the root in the x direction, and we're going to have some force from the strut. And the angle between the strut and the wing is 31 degrees. Our loading is the same equation we had before. So this one is a bit messy, and I think it's worthwhile to find those reaction forces up front. So we're going to assume that there's some equivalent force that we can calculate that we can use to calculate our reactions. I'm going to go through this pretty quickly because you guys should have this down pretty quick or pretty pat. And if there's something I go too fast, just stop the tape. Uh, Go back and figure it out. There's going to be a y component and an x component to that force. Um, the magnitude of that equivalent force, call it F sub L, is equal to 1/2 our base of the triangle, which is 12, times the height of the triangle, which we said was 108, and that's equal to 648 pounds, which is the answer we got before. The location of that load, L sub x, is 1/3 of the 12 feet. That's equal to 4 feet, which we got before. So to find the force on the strut, we can do the sum of the moments about our root equals 0, sum of the moments of the roots equals 0, and that's equal to the 648 pounds equivalent times the 4 feet minus the force of the strut, F sub S y, times 5 feet, and that gives us a F sub S y equal to 518.4. From the geometry, we know the F sub S equals the 518.4 over the sine of 31 degrees, and that gives us 1,006 pounds in the strut, and that is going to point that direction. This points downward. And we can also, while we're at it, determine that the in the strut in the x direction is equal to 1,006 pounds times the cosine of 31 degrees, and that's equal to 862.3 pounds to the left. And since that's the only force with an x component, it's pointing to the left, 862.3. We can, by inspection, determine that this is 862.3 pounds pointing to the right. The sum of the forces, y equals 0. I've got my lift of 648. I've got the y component of the force in the strut equal to 518. That doesn't look like a 5. 518.4 downwards minus f at the root in the y direction, and this gives us our phi equal to 129.6 pounds downward. Okay, so those are our reaction forces. 129.6. 129.6 is that one. So we've got all of the forces, x's and y's, and we can now do our analysis. For the normal forces, again, by inspection, we've got that minus 862.3 force, and it's negative because it's in compression by our conventions for internal force between the root and the strut, and then beyond the strut it's just 0. So I won't spend any more time on that. So let's work out the rest of our stuff. As before, their change in shear is a function of the integral of the load. And look at it as a delta shear is the integral of the load, plus we'll have some initial conditions. We determined that the lift is that equation, which we'll substitute into the load here. The forces at the root, we had minus 129.6 in the y direction and minus 518.4 in the y direction downward at the strut location, x equals 5. So we're kind of going to have to look at this maybe in two pieces because there's something funny happening in the middle. But if I do the, if we just start from the left and I do the integral of my lift or the load, I get the shear of, I get my shear v of x equals the integral of 108 minus 9x dx plus our initial conditions, and that's equal to 108x plus 4 point or minus 4.5 x squared plus our initial conditions. There's nothing new here, right? It's the same stuff here. Well, I know at the root, x equals 0, my shear force that results from the reaction at x equals 0, my shear force is uh, equals minus 129.6. So I know that if I substitute 0 into this equation, I get my initial conditions there, and I get my shear force V of x equals to minus 129.6 plus 108x minus 4.5x squared. And that applies when we're to the left of that strut, okay? It's at x less than 5. Now, when we get to that strut, there is, in theory, a point source shear applied. Actually, it's applied over a small distance, but we'll assume for convenience that it's a point force. So at x equal to 5, I'm adding a minus 518.4 pounds downward, okay? That's this right here. So I'm going to have to add that. That gives me a step change in my shear force, so that's going to be added as we get beyond x equals 5. So at x greater than or equal to 5, we're going to add that 518 to the negative 518 plus our existing initial value here of minus 129.6 gives us a minus 648. And the rest of the equation is the same, plus 108x minus 4.5x squared. And that's at x greater than or equal to 5. Okay, so there's our shear. It's got that step in like we'd expect. And if I go to the next slide, we can see the results here. We know that this is minus 129.6. This component here is minus 518.4. And so I have my 518.4 pounds discontinuity in the shear diagram. I start out at that minus 129.6 right there. The shape of the curve in between is the same as the shape in the previous example, but of course we've got that step in it. And here is my equation written out neatly for those that have trouble with my handwriting. Next, we got to find the bending moment, right? So again, the moment is the integral of the shear plus our initial conditions, or we could say that the change in the moment is the integral of the shear over some specific, between two specific points. We also know that at x equals to 0, let's go back a couple slides. Actually, one slide is enough. At this point here, there's no moment there. We said that was a pinned joint. So our moment at x equals 0 equals 0. So our moment at 0 equals 0. So that's going to give us our initial condition of 0 at that point. So if we do the integration, and I'm just going to skip the intermediate steps, I'm going to say that my moment equals uh, minus 129x plus 54x squared minus 1.5x cubed plus our initial conditions. This is for x less than 5. And you've seen this equation before. And we know that at x equals 0, our moment is equal to 0, so that initial condition is equal to 0, and I can just take that away, okay? Beyond that, for x greater than or equal to 5, we have the initial condition, whatever it is, minus 648x plus 54x squared minus 1.5x cubed for x greater than or equal to 5. And what we don't know is our initial condition. And we can't look at x equals 0. We could look at x equals 12 and say, well, at x equals 12, this whole equation has to be equal to 0. Or we can look at what happens at 5 feet, okay? If I take my first equation, the top equation, and evaluate it at x equal to 5, I get minus 129 times 5 plus 54 times 5 squared minus 1.5 times 5 cubed, and that gives me 517.5 pound-feet of moment at x equal to 5 feet. And I know that, at x greater than 5, less than 5, right around 5, it's going to be that value on both sides of that. The application of a force at a point does not cause a step change in the magnitude of the moment. It causes a discontinuity in the slope, but the magnitude on either side of that loading is going to be the same. And, if I had applied a couple at that point, then I'd get a step change in moment. We don't have any couples in this problem. So I know that if I take my second equation, that the moment equals that 517.5, that's going to be equal to my initial condition for the second equation, minus 648x plus 648 times 5 plus 54 times 5 squared minus 1.5 times 5 cubed, and that's run all that through, I get my initial condition is equal to 2595. Okay, and I'll write out the final equation on the next slide because I put it there anyhow, and rather than rewrite it, you can read it. So here are our equations for the moment. Here, those were based on integrating the equations from the shear and finding those initial conditions. And we had kind of funny initial conditions, at this point right here in the middle. But you can see that we start with a moment of 0. We end with a moment of 0. We had a pin at the left, and we just had the beam ending with no forces and no reactions on the right. There's the discontinuity in the shear, which results in a discontinuity in the slope. We also note that where the shear crosses 0, that's a local minimum in our moment, as we'd expect. Right there, the slope is equal to 0. We have a maximum. And I think that's pretty much all I need to say about this. There's one more slide I wanted to touch on, and this is the two systems compared. The top one was our cantilever, and the bottom one had the strut. Obviously, the shapes of these curves have some changes, but the things we should probably notice here, for our cantilever, we had a minus 648. That's pretty illegible, isn't it? Minus 648 was our maximum shear load. The maximum shear load with the strut was 297.3, so we reduced the maximum shear in our thing. The moment here for our cantilever was 2592 was the maximum value. With the strut, we only had 517.5. That's almost an 80% reduction in the maximum bending moment. So you can see why putting a strut in this kind of structure is attractive. From a structural perspective, if you're trying to keep weight down to support a particular load. So in both of these cases, we're supporting the same airplane with the same aerodynamic forces, but we've got a lot lower maximum load here when we put that strut in. So I think that's everything I needed to show in this example. Hope you found it useful, and I'll see you next time. Bye.